Hey everybody, we are going to continue with our hypothesis testing, and this time we're going to test a claim about a mean. And for these two examples that I'm going to be going through, it's going to be very calculator heavy, but specifically the population standard deviation is not known. This means for sure we're going to be using a t-test. The requirements, simple random sample, and if it's normally distributed, it doesn't matter. If it's not normally distributed, n has to be bigger than 30. And we're going to just jump into this. Listed below are measured radiation emissions corresponding to a sample of different cell phones. Assume that the sample is a simple random sample, so it meets our first requirement. And the population is normally distributed, so we've met our two requirements. Now, if you look back on our sheet, we had two of them for mean. One was if we did not know this population standard deviation, which we don't in this case. And if we did, we would use the z-test. And so here's our test statistic, but I'm going to show you something. And we could calculate the test statistic that way, but that's fine. What I'm going to show you is how to use your calculator. So you go to Stat, and you're going to edit. I've already put mine in, so you'll have to put these 11 pieces in. So you may need to pause the video to do that. And then I'm going to go over to Tests, and you can see there is a t-test. And I have two options. I can use a list, which I just put my numbers into the list, and so did you. Before I get all that, let's do our null hypothesis. That the mean, remember the null is always equals. And they want to say that the radiation level is less than 1, so mu is less than 1. And I want to set up our picture. And less than means that it's going to be a left-tailed. And they give us our alpha, 0.05. And I'm going to figure out our critical value. So inverse norm, 0.05. Negative 1.64. Negative 1.64. Now, what I want to show you with the calculator, which is super cool, is once we put the data into the list, I go over to tests and the t-test. And if I didn't have raw data, then I wouldn't use this. But here, my mu is going to be 1 in this case. The data is already in list 1, frequencies stay 1, and in this case, it's a less than here. And look how cool this is. Go. It gives us not only our t value, but the p value as well. So we have that. Our t value is about negative 0.48, and our p value, which is more important, is 0.3191. Calculator does all the work for you. I'm going to show Casio in just a second. I wanted to, so negative 0.48, maybe it's about there. And that means that all of this area, all of it, all the way down, is about 0.32. That is so cool that it does all that work for you. Before we come to a conclusion, I want to show Casio real quick. Casio, you have to actually change your menu and go to menu 2. Again, I've already put the data in to list 1. I'm going to go to a test. That's a t-test, a one-sample t-test. And I can choose a list or variable. I put mine in a list. This is going to be less than. It's going to be 1. And I'm using list 1. And there you can see it's the same t value and the same p value. I will be using the TI for the rest of these since most people have a TI. But the cool thing about this is it's very clear to see that we're not going to reject the null hypothesis. You can see that the p value is significantly larger than our alpha, which is 0.05. So we are going to fail to reject our null hypothesis. So there is not sufficient evidence to support claim that the level is less than 1 watt per kilogram. Pretty cool, and the calculator does all the work for you. Next up, we have a sample of 106 body temperatures with a mean of 98 So this is the sample. This is all sample stuff, including the standard deviation. Again, it can get confusing. You see standard deviation here, and then up here we say that the standard deviation is not known. Again, this is the population standard deviation. This is the sample standard deviation. So they want us to do a null hypothesis that the mean body temperature is 98.6 degrees Fahrenheit. And they want to know that the mean body temperature is here, so that means not equal to 98.6. And I'm going to make this the claim, even though it's not really worded that way, but we're going to do that anyway. So we're going to draw our picture. And if you remember, not equal to means that we split into a two-tail. So each of these get half of the alpha, which in this case, 0.025. That's our critical region. And we can do inverse norm to get our critical values. Negative 9999, comma. Oh, no, I'm sorry. This should be inverse norm. Inverse norm. And area to the left, 0.025, negative 1.96. Which makes this also 1.96. And I'm going to go here and go into stat again to tests. This is again a t-test. And this time I don't have the data. I have the raw statistics. So here is going to be 98.6. X bar they have here, 98.2. Sample standard deviation is 0.62. And N is 106. This one's not equal to. And calculate. And very beautifully, it just gives us our data. So this says that our test statistic, T, is negative 6.64. And p-value is, the way you would read this is 1.4 times 10 to the negative 9th power. That actually means I'm going to move that decimal 9 places this way, which means it's a super, super small number. So that means negative 6.64. And basically the area here is 0. So our conclusion is the p-value is definitely less than our alpha, which is actually it's alpha over 2. We can use 0.025 to compare directly. It doesn't matter. It's so far beyond it. This one's definitely reject the null hypothesis, meaning the average body temperature is definitely not 98.6 degrees Fahrenheit like most of us grew up learning. So our conclusion is we're going to reject the null hypothesis, and there is sufficient evidence to support the claim. that cardiac temperature is not 98.6 degrees Fahrenheit.